Lines of Charge lab, which is really just a continuation to the previous lab about charged tape. So the goal of this lab is to determine the amount of excess charge on the tape to within an order of magnitude, but here we're going to be modeling the tape with a line charge instead of a point charge like the previous lab. And we're going to be comparing the results between the two, and ultimately we will see that the net charge on the tape using the line charge model is determined to be greater than the net charge on the tape from the point charge model. And so in this lab, we'll be going over a review of the previous lab, some physics ideas, the models, and the results. So to charge a piece of tape, what we did is we put one piece of tape on our table, and then we put another piece of tape on top of that one, and we quickly pulled the upper piece of tape off. And we can see that this charges the tape because if you bring your hand next to it and check for attraction, there's going to be attraction. Now your hand is neutral, but the presence of charge on the tape will polarize your hand and create an attraction between the two. We also know that the tape is positively charged because of the pen test, which is where we take a negatively charged pen and we hold it next to the tape and we check that there is attraction. And so once we have two pieces of charged tape, we find that they're about equal length with mass, and we suspend one piece of tape between the two objects of the same height, and we bring another piece of tape closer from underneath the first piece until the first piece begins to float. And then we can measure the distance between the two tapes when the floating starts. Now there are a couple of simplifying assumptions we made when we did this last lab. Last lab we treated the two pieces of tape as point charges with all the charges concentrated at the center of the tape. Now this time we are not doing this. This time we are treating the two pieces of tape as line charges, with their charge spread across the entire line. We are, however, still assuming that the two pieces of tape have identical charges, because they were charged using the same method, and at least we know that they have the same sign, because they're repelled from each other. Now, there are some physics ideas important to this lab. Newton's second law states that if there's no change in momentum, there is also the net force is also zero. And we know that the forces acting on the top tape are the gravitational force and the electric force due to the bottom tape. So the top tape's not moving, there's no change in momentum, and so the gravitational force and electric force are equal and opposite. We can calculate the force of gravity using the same formula as before, but this time, instead of treating it as one point charge, we're going to be calculating the electric field of many small point charges along the entire length of the tape. And that's how we're going to be modeling it as a line charge. We also have Coulomb's law, which states that opposite charges attract each other and like charges repel each other. And so now this is the model for this lab. As you can see, we have our constants. We have the formula for electric field of a particle. And then we take the two tapes and we break them up into many different small particles, and we sum up all the net electric fields by all the particles to find the overall electric field and the overall electric force. And once we do this, we have successfully modeled the two tapes as line charges. Now, as you can see, we need to make sure that the magnitude of electric force equals the magnitude of gravitational force, because that means that the net force is zero, and that accurately models that our tape is not moving. And so we use the guess and check method to keep modifying the charges on the tape until we achieve this result. And using this method, we can see that the charge of tape from the point charge model, which we did previously, is 5.6 times 10 to the negative 9th coulombs. And the charge of tape from the line charge model, which we have now, is 1.7 times 10 to the negative 8th coulombs. So it's about a 3-time difference. The line charge is about 3 times, the line charge model gives the charge that's about 3 times stronger than the point charge. And so the point charge model is underestimating the actual charge of the tape. Now, why do these estimates differ? These estimates differ because the point charge model assumes that the charges of the tape are separated by the distance between the tapes only, while the line charge takes into account the charges being spread along the entire length of the tape. So many of the different small charged particles are distant to each other by more than just the vertical distance, and so the overall effect is that the increase in distance decreases the electric field, and so to make the electric force equal to the gravitational force, we require more charge on the tape. Therefore, the overall charge modeled by the line charge model is bigger than the point charge model. And the line charge model is more likely to be close to the real value because it more accurately simulates how the tape is actually in real life. It's not one particle, it's an entire length. Alright, that's it for this lab. Thank you for watching.